In the previous video, I calculated the magnetic field due to a rotating charged sphere. It turns out this is kind of a big deal because a rotating charged sphere has a magnetic dipole moment. And then we can use that to say, well, electrons have magnetic dipole moments, so maybe they're charged rotating spheres. They're not, but maybe they are. But I'm going to show you why they're not. I'm going to show you why an electron is not a rotating sphere. So the spin is something that is not really spin. Okay. So this is what was originally done. I think it was Pauli did this, but I'm going to do the same thing. So we need to calculate the magnetic dipole moment for the rotating charged sphere, and then use that with the known magnetic dipole moment for the electron to find out how fast it'd have to rotate. Okay. We define the magnetic dipole moment for a loop of current as the current multiplied by the area vector, which is a vector with the magnitude equal to the area and in the axis perpendicular to the area. Okay. There's other ways to calculate it, but that's what we're going to use now. And so if I have this spinning sphere, then I can break it into rings like we did before, and each one of those rings is a tiny little bit of current. And so I can calculate the magnetic dipole moment for each ring and then just add them all up. So that's what we're going to do. So there's my M. They're all going to be in the z direction, so I only need the z direction. So I can write this as dm is equal to di A. So A is the area of each loop. Di is the current in each loop. So we've got to calculate the current in each loop. Now, we did this before, and there's a couple ways to do this. I'm going to say that this has some uniform charge density. Sigma is Q over 4 pi r squared. And then di is going to be equal to the surface area current, which is current per length. So that's going to be equal to sigma v. And then I have to multiply that by the length that it passes through. So what's the length of this little piece right here? Well, the length of that piece is r d theta, right? Because this is r, and d theta is my integral that way. So it's a d theta. Now I just need to get an expression for v. So v is omega times r, where that's the radius of the coil of the particular loop that I'm in. So that r is going to be equal to r sine theta, right? So here's my right triangle. If that's r, then that's going to be r sine theta. So if I plug that in, I get di is sigma omega r sine theta r d theta. So we can write that as sigma omega r squared sine theta d theta. Okay, so that's kind of important. That's half of what we're doing. So let's put it over here. Di is going to be equal to sigma omega, and we can get sigma in terms of q, which we will later, r squared sine theta d theta. And let's put a box around that in a color. Because once you put the box around it, then it's got to be correct, right? So let's just fix that theta. Theta. Okay. Now we need to get the area. Well, that's not too hard, right? So the area is just going to be pi times the radius of each ring, which is r. So it's going to be pi r squared sine squared theta. So A is r squared sine squared theta. I'll put a box around that one. Look, it's going to be in a different color. See, I bought these colored chalks. Now I know dm, and I can integrate to find the whole m. That's what we're going to do. And hopefully I won't make a mistake like I did last time. Okay, so m is going to be the integral from theta is 0 to pi of I dA. So I have sigma omega r squared sine theta. Let's put the d theta at the end. And then I'll put this one r squared, so I have r to the fourth, sine squared theta, so I have sine cubed d theta. That's the exact same integral we had before, but let's just do it again anyway. So I'm going to write this as, I'm going to say sine theta cubed is equal to sine theta times, run out of room. That's what I'm going to say. I'm going to say run out of room. Not going to run out of room this time. Sine cubed theta is sine theta times 1 minus cosine squared theta. So I can write this as sine times sine squared, and sine squared is 1 minus cosine squared. Then I can make a u substitution. U equals cosine theta. So du is negative sine theta d theta. So if I make that u substitution up here, I get m equals, pull the things out front, sigma omega r to the fourth, and now I'm integrating of negative, right, because I have a negative du, 1 minus u squared du. Well, that's pretty easy to integrate. So it's going to be equal to negative sigma omega r to the fourth times u minus u cubed over 3. Now we need to evaluate the limits. I'm going to go ahead and find u1 and u2. So u1 is going to be u when I put theta is equal to 0. So theta 0 is 1. And then u2 is going to be when I put in theta is pi, so I get negative 1. So I'm going to integrate from 1 to negative 1. So if I do that, I get m is negative sigma omega r to the fourth. And I'm going to put in u at u2, which is negative 1 minus a negative 1 cubed, which is negative 1, so plus 1/3. And then I can say subtract this, so I get minus 1. And then I get minus a negative, so plus 1/3. So this is going to be equal to, I'm going to factor out the negative, sigma. I did run out of room. Look at that. OK, let's just put it up here. We're almost done. I have trouble evaluating limits sometimes. So m is going to be sigma omega squared r to the fourth. And then I have 1 plus 1 is 2 minus 2/3. And I think this is where I made my mistake before. So let's just, I'm not going to skip. I was like, I'll just do that in my head. Don't do it in your head. So it's going to be, get a common denominator of 3. So this is 6/3 minus 2/3 is 4/3. Oh, that's not 4/3. That's 4/3. OK, now let's get the whole answer. And we don't want it in terms of the charge density, so I'm going to put in everything. So m is going to be sigma, which is q over 4 pi r squared, boom, omega squared, r to the fourth, 4/3. That cancels, and I get q r squared omega squared. Is it omega squared? No, it's just omega. I don't know where I got the omega squared. Over 3 pi. Did the pi not cancel? The pi should have canceled. Where did I lose my pi? So that's sigma. Pi with the area. I had a pi up there, pi r squared. So there was a pi, so that cancels. I'm so sloppy and I apologize. So this is the answer, m. I'll put it in white. I need to put it in a color. OK, there's no pi. Now we have the dipole moment for the electron. They always write this as mu e, even though here we're using m. I think it's the same thing. I have 9.28 times 10 to the negative 24 joules per Tesla. And then I need to know the radius of the electron. I'll call this Re. And of course, we don't have a value. There's actually a classical electron radius value that's a maximum amount. We're going to use that one. It's 3 times 10 to the negative 15 meters. So let's use these. And I want to calculate the velocity. Okay, so I can calculate the angular velocity by setting this equal to this, and then putting this in for my radius, and then I'll solve for the velocity. But let's just do all that in Python, okay? Because we're going to have to use crunch some numbers. So I'm switching over here to Python. You can use a calculator if you want. I need the charge. E is 1.6 times 10 to the negative 19th. mu e is, what did I just say? 9.28 times 10 to the negative 24. Re is 3 times 10 to the negative 15th. What other values do I need? Q, R, oh, I have that. Okay, so let's just say if I solve for omega, omega is going to be equal to 3m over q r squared. So let's put that in. Omega equals 3m, 3 times mu e. Why can I not remember that? Divided by q, which is going to be e, times re squared. Let's go ahead and print omega. And this is in radians per second. Okay, so 2 times 10 to the 25th radians per second. That's pretty fast. Now if we solve for the velocity, so the velocity is going to be omega times r, re, print v equals, this is the outer part of the biggest part, v in meters per second. 6 times 10 to the 10th. 3 times 10 to the 8th is the speed of light. So this is faster than the speed of light, so we know that can't work. So that's why we know that the electron, the magnetic dipole moment of the electron, is not because it's a spinning charged sphere. The end.